Welcome back, everybody. Okay, so it's been 1 week in the complex wilderness, and today I am ready to tell you about one of my favorite properties of complex functions. So I'm going to define what it means for a function to be analytic. And analytic functions are essentially well-behaved functions that we can do calculus on. Okay, so we're used to doing taking derivatives and doing integrals for real valued functions, and we would like for all of that to carry over to complex functions, because again, remember, these complex functions are going to be how we represent the solutions of ordinary and partial differential equations, so we need to be able to take derivatives and integrals and do calculus. And some functions in the complex plane are actually pretty wild and poorly behaved and break our intuition of what it means to be able to do calculus. So some functions are better behaved than others, and the well-behaved functions that we can do calculus on are typically called analytic functions. Okay, so specifically we're going to be talking about analytic functions. Okay, analytic functions. Very, very important class, especially for solving partial differential equations. So a function, and I'm going to define it, then I'm going to give you an example of a non-analytic function to show you how things get weird, and then I'm going to give you conditions to know if a function is or is not analytic. So a function, let's say f of z is analytic, and I'm going to use red for this, is analytic. And we typically say it's analytic in a certain region of the complex plane. So in a domain is just a region. It's math speak for some set in the complex plane. Some domain D in the complex plane. It could be equal to the complex plane. It could be the whole plane, or it could be a little subset. So if I have my complex plane, then my domain is just some little region where I'm talking about, some subset. A function f of z is analytic in that domain D if f of z is single valued. Remember, the logarithm was infinitely valued. So if f of z is single valued, like the cosine and sine functions are single valued, z squared is single valued. Z to the 1/2 is not single valued. There's two solutions to z to the half. If it's single value and has a finite derivative, f of z, f prime of z, everywhere, or let's say for every z in that domain D. Okay, this is just curly D. Sorry, it looks so squiggly. That's my fancy pants D. Okay, so this is just math words, and these are the conditions. I'm going to show you that these are the conditions for that function f for it to be well behaved enough for us to do calculus on. We can take derivatives, and they mean something intuitive to us. We can do integrals in that domain D, and there are special nice properties. If f is single valued and there exists a finite derivative at all points in that domain. So we're talking about points z that are inside this domain. That's what this is in math speak. Z is an element of the set D, the domain D. Okay, so we already know about functions that are not single valued. Z to the 1/2 has 2 values. Z to the 1/3 has 3 values. Log of z has infinitely many values. So those are going to kind of break immediately this definition of analytic, and calculus is going to be weird, or at least slightly different on those functions. Functions like z squared are going to be fine. So it has to be single valued, and it has to have a finite derivative for every z in the domain. So specifically, the derivative can't be infinite. It can't be like, the function 1 over z is going to blow up at z equals 0. It has an infinite derivative. And the derivative is going to have to be the same no matter what path I take that derivative in. Okay, so I'll tell you what that means in a minute. Good. So this is a kind of the definition. And what I want to do now is I want to give you an example of a non-analytic function to show you the kinds of weird things that can happen in the complex plane. So a non-analytic function, not analytic, function would be f of z equals the complex conjugate of z, which we call z bar, which is equal to the real part minus I times the imaginary part. So instead of x plus iy, which is z, the complex conjugate is x minus iy. And I claim that this function is not analytic. We are not going to be able to do normal calculus. And in fact, what I'm going to show you is that the derivative doesn't exist uniquely. It doesn't have kind of a unique, well-defined derivative of this function. It's a weird function, okay? So let's see. I think what I want to actually show you is we're just going to compute the derivative, and I'm going to show you that weird things happen. So we're going to take df dz. And remember that the definition of a derivative is essentially this kind of infinitesimal rate of change of f as I vary z. So this would be kind of the limit as delta z goes to 0, so my infinitesimal delta z goes to 0, of f of z plus delta z minus f of z divided by delta z, okay? This is just standard, freshman calculus, kind of this is how we always have defined the derivative. This is how we're going to define the derivative in the complex plane too, totally legit. And so, that's essentially the limit of, let's say this is the limit as delta z goes to 0 of z bar over delta z. That's just, f of z is, I'm sorry, I should have said, this is delta z bar, delta z bar over delta z. You can convince yourself that if you plug in z plus delta z to z bar and z to z bar and subtract them, what you're going to get left is a delta z bar, a complex conjugate of delta z. And this equals the limit as delta z goes to 0 of delta x minus delta yi over delta x plus delta yi. Good. So the derivative df dz is the infinitesimal rate of change of f when I vary delta z. And if you literally plug in z plus delta z and z into this complex conjugate function f and cancel them out, just do that on a piece of paper, pause the video and do that, you'll see that the top is going to be delta z bar, and the bottom is just delta z, and we're going to take the limit as delta z goes to 0. And it's equal to this quantity here, okay, where delta x is how much I vary in the x direction, delta y is how much I vary in the y direction. But this is where it gets really weird, is that this derivative is totally different if I take delta z infinitesimal in the real direction versus if I approach infinitesimal changes in the y, or the imaginary direction. So that's what I'm going to show you here. Okay, so, and let me just define, so we're going to, let delta z equal delta x plus I delta y. That's what we define delta z here, delta x plus I delta y. And delta z bar equals delta x minus I delta y. That's what we have on the numerator, okay? So now what we're going to do is we're going to look at this function as we approach this derivative, as we take this delta z goes to 0 in different directions, okay? And so essentially this delta z, I'm just going to draw a picture here, actually. I think this is going to make it a lot clearer. So this is the real part, this is the imaginary part. Let's say that my point z is right here at the middle. And what I'm going to do is I'm going to look at case 1, where I take delta x goes to 0. So I'm going to start on the real axis and approach as delta x goes to 0. And then case 2, I'm going to freeze the real part to 0, and I'm going to take the limit as delta y goes to 0. And for the derivative to make sense, those two limits should be the same thing. Okay, so regardless of how I approach delta c goes to 0, this derivative should be the same thing no matter what direction I approach delta z equals 0. Okay, and so if we write this out, so if we say, let's say approach, delta z goes to 0 from the real axis, which means delta y starts out being 0, and then I take the limit as delta x goes to 0. This is case 1. Then that means the limit, this expression becomes limit as delta x goes to 0 of delta x over delta x. That equals plus 1. Okay? So the derivative of this function, if I started with delta y 0 and I take the limit as delta x goes to 0, I approach from this direction in case 1, my limit equals 1. So this, in case 1, this directional derivative is equal to 1. Let's look at case 2 when I approach in the imaginary direction. Case 2, when I approach, sorry, it's squeaky, when I approach delta z equals 0 from the imaginary axis, so I start off with delta x equals 0 and I take the limit of delta y goes to 0. Now I have limit delta y goes to 0, and now remember delta x starts at 0 and I'm taking the limit of delta y goes to 0, but here I have minus delta yi over plus delta yi, and if I take the limit as y goes to 0 of this, I get minus 1. The i's cancel and the delta y's cancel, and I get a minus 1. And so this is super duper weird, okay? This function, the complex conjugate of z, the function f of z equals z bar, does not have a well-defined derivative. It does not have a derivative that is independent of the path of approach that delta z goes to 0. So we know that this is the definition of a derivative, that the limit as my infinitesimal change goes to 0 of the change in f over that change in z. But because these complex functions have a real part and an imaginary part, I can take that limit, this derivative limit, I can take that limit approaching from the delta x direction or from the delta y direction. I can approach from any other angle and I'll get different derivatives. That's also super weird. I can approach from other directions. It's just that these are the easy ones to compute. And because of the way that this complex conjugate function works, if I approach from the delta x direction, I get plus 1 derivative. If I approach from the imaginary or the delta y direction, I get a minus 1 derivative. So this function does not have a well-defined derivative that exists at every z. Like which one is it? This doesn't have a derivative. It depends on the path. So this is an ill-defined expression here. This is multi-valued. It doesn't exist. So this is a weird function that's not analytic, and calculus is difficult because now the derivatives I take depend on the path I'm taking, okay? And so it doesn't have just an f prime of z. I can't write df dz. I have to specify which direction I'm taking that derivative. I can only specify directional derivatives for this function. Good. So that is a neat and kind of intuitive example of what can go wrong in the complex plane. So this is a non-analytic function. And so now I'm going to revisit what does it mean for a function to actually be analytic. So these are some conditions for a function to be analytic. Now we're going to start deriving what are the outcomes, what are the kind of implications of that. And I will conclude by giving you some canonical examples of functions that, yes, they are analytic, and some canonical examples of functions that, no, they are not analytic, okay? And I'm almost feeling like I should just tell you some examples of functions that are analytic first. Maybe that's what I'll do. And I'll do those in blue. So I'll just do some functions that, yes, indeed, they are analytic. So analytic functions, analytic f of z, would be things like any polynomial. So polynomials z to the n for integer n, for n equals 1, 2, 3, ... Okay, not for n equals 1/2 or 1/3 or 1/4, because those are not single valued. Polynomials, monomials, sums of monomials, polynomials, things like that. Those are in fact analytic functions. Yes, indeed, they are analytic. Maybe at the very end of this video, if I remember, I'll just take the polynomial z squared and we'll do this exact same limit, and I'll confirm for you that yes, in fact, it satisfies this property that the derivative does not depend on the direction. So I'll probably put chapters in this video, and you can fast forward if you want to see me derive that yes, z squared is in fact analytic, and that the directional derivatives equal each other no matter what direction I come in from. Polynomials, other functions that are good ones. So this is kind of one huge class. Another big class are functions where the Taylor series exists. That's kind of a vague way of saying it, but I'm just going to say functions kind of with a Taylor series, a well-defined convergent Taylor series. And those would be functions like, e to the z, or cosine of z, or sine of z. We know that these are convergent functions. They have a convergent Taylor series for all points z in the complex plane. In fact, these functions, polynomials and e to the z, cosine of z, sine of z, these are not just analytic in some small neighborhood d, they're analytic everywhere in the complex plane. For every single point z you can name, these are analytic at every point. Which again, I told you in a previous lecture, the name for that in complex analysis and mathematics is called an entire function if it's analytic everywhere. Okay, if you can do calculus absolutely everywhere. And then actually there's kind of a fun 2.5 case where this is like platform 9 3/4. So this is kind of a halfway case. The log of z, the log of z on its principal branch, on principal branch, let's hope this doesn't, on its principal branch. So remember this function, the imaginary part, kind of forms this spiral staircase. If I just take the first branch of this thing that goes from 0 to 2 pi, then that log of z is single valued on that branch. So if I only define the log of z on that principal branch, then that is actually analytic everywhere except at z equals 0. So this is analytic for all z not equal to 0. Okay, so it's analytic almost everywhere. It's not an entire function. It does have this weird non-analytic point at the origin. So if I do a contour integral around that point, weird things will happen, and I'm going to show you that in this lecture at the end and in the next lecture. And in probably all of the next 5 lectures, we're going to talk about that single weird point where this is not analytic is very important. But it's analytic almost everywhere. It's analytic on large swaths of large domains of the complex plane that don't encompass that origin. So in fact, this place, this domain that I drew here, log of z is analytic on that domain if I'm only considering the principal branch that goes up one flight of that spiral, that infinite spiral staircase. So these are functions that, yes, indeed, they are analytic. And now I'll just give you a few examples of weird functions that are not analytic. So not analytic would be things like z bar. So things like z bar where the derivative is different at different directions. So anything that has a singularity, so any function that has kind of a singularity where this goes to negative infinity, so any singularity, the function is not analytic at a singularity, so things like 1 over z are going to give us lots of trouble. If I have a cliff, if I have like a cliff in my complex landscape, so I'm from Texas, and in Texas we have the Llano Escarpment in West Texas, where if you approach at this point, it kind of drops off maybe 1,000 meters and there's a cliff. So cliffs are not analytic because the derivative would be infinite at that cliff and it would not exist. It would not have a finite derivative at that cliff. Okay, the function log, if I don't consider it on this principal branch, is also not analytic because it would be infinitely valued. The function z to the 1/2 is not analytic because it's infinite. It's not infinitely valued. It has 2 values. It's not single valued. Cusps also, if I have a function that has a really sharp cusp, and in fact, kind of z bar, if you might actually want to fire up MATLAB or Python and plot the real and the imaginary parts, and you'll see that this function is actually a bit cuspy. And that's kind of a weird thing, is that it's cuspy depending on what direction you approach the function in. And kind of my rule of thumb for non-analytic functions is it tends to be functions that cannot easily be represented as a closed form of z. So z to the n is kind of only written in terms of z, and if I did f prime, it would be n z to the n minus 1. That's like a well-defined derivative. Same with e to the z, cosine z, sine of z. But z bar can't be defined as a primitive function of z. It can only be defined in terms of the real and the imaginary parts of z. Same with logarithm, actually, right? We can't really write log of z as some, primitive expansion of z. We need to write it in terms of the real and the imaginary, or the magnitude and the phase of z. And so that's kind of another rule of thumb I use, is if my function can't be written as a simple function of z, but I need the real and the imaginary parts to specify this, usually those functions are not analytic. Okay, good. And again, as a general rule of thumb, if I just randomly pick a complex function, out of a hat, chances are 99.9999999% of the time, it's not going to be an analytic function. The vast majority of functions, if I just randomly generate a function in the complex plane, it's not going to be analytic. So analytic functions are very, very special. In math, we call this measure zero. They're a measure zero set in the space of all functions. They're extremely rare, special functions where you can do calculus. Good. Okay, so now what I'm going to do is I'm going to derive the Cauchy-Riemann conditions for a function to be analytic. And this is in terms of partial derivatives. It's an extremely powerful expression in math, and it ties these complex functions to partial derivatives. It's one of the most important conditions or relationships in all of complex analysis. It's kind of one of the cornerstones of complex analysis. So this is super important. Okay, so the Cauchy-Riemann conditions. Okay, so for a function to be analytic, we need for its derivative to be the same no matter what direction I approach that derivative. Okay, so I'm just going to write this out. For a function to be analytic, the derivative must be the same from the two paths taken on the real and imaginary axis. For a function to be analytic, the derivative must be the same for the two paths on the real and imaginary axes, kind of what I drew down here. If I take my derivative and the delta x goes to 0 direction or the delta y goes to 0 direction, those have to be equal. Now this, you would need to do some proof. This is a theorem. You would need to prove that theorem that if this is true, if these are equal on the real and the imaginary axes, then it's real from any approach angle, for any way that I could possibly approach delta z goes to 0. If the delta x limit equals the delta y limit, then this is true for any approach angle delta z goes to 0. That's something you would need to prove. we're going to say if that's true, then this function is analytic. That's kind of the Cauchy-Riemann hypothesis. And so what we're going to do is we're going to define our f of z equals, it has a real part, u of x comma y, and an imaginary part, I of v of x comma y, where, of course, z equals x plus I y. Okay, so this is going to be the function we're going to take the derivative of. It has a real part and an imaginary part. And this is the z that we're going to take the infinitesimal limit of delta z goes to 0. Okay, which means we're going to take delta x goes to 0, delta y goes to 0, and we're going to kind of derive what conditions have to be true. And I'm going to give myself a little room for my head. So df dz, again, exactly like what we wrote down here, is the limit as delta x goes to 0 and delta y goes to 0. That's the same as saying delta z goes to 0. Both of these have to go to 0. They could start at 0, as in these two cases, or they could start both non-zero and go to 0 any way we like, of delta u of, well, let's say delta u. It could be, of course, it's delta u of x comma y, but let's just say delta u. Delta u plus I delta v divided by delta x plus I delta y. Again, you can pause the video and actually plug in x plus delta x, y plus delta y, v of x plus delta x, y plus delta y, and expand that out in a first order Taylor series and cancel out the f of, like the terms that are not plus delta z, and this is what you're going to be left with. So you can expand that out in a Taylor series f of z plus delta z, expand that out, subtract f of z, and this is what you're going to be left with up to first order. And we're going to, again, divide by delta z. Okay, so you can pause and verify that this is what you get when you plug this into this expression and use the Taylor series. And now what we're going to do is we're going to take this, and again, we're going to take it approaching from the real axis, from the delta x goes to 0 direction, and from the imaginary axis, from the delta y goes to 0 axis, and those have to be equal for this to be an analytic function. So kind of, approach 1, again, is kind of on the real axis, which is the delta y starts out being equal to 0, and we say df dz equals limit as delta x goes to 0. Delta y was already 0 because we're starting on the real axis. Delta x goes to 0, the limit of delta u plus I delta v over delta x. Now this is kind of fun. Because we froze y equals 0, delta y equals 0, and we're approaching on the real axis, this derivative here is actually a partial derivative. The limit is as delta x goes to 0 for y frozen of delta u over delta x. That's the partial of u with respect to x. So this is partial u partial x plus I partial v partial x. This is super important, so I'm going to put a little, well, maybe I'll bracket that in a minute. This is super important. So if I take the derivative on the real axis of this function, I get partial u partial x plus I partial v partial x for whatever u and v happen to be. This is going to be what that derivative is. In fact, you can verify, here f of z, u is x and v is minus y. And so you can actually compute what these are, if you like. And now we're going to compute what is the derivative if I approached on the imaginary axis, if I froze delta x equals 0. So now what we're going to do is we're going to approach on the imaginary axis as if delta x was frozen at 0. And so df dz equals limit as delta y goes to 0. Now delta y goes to 0 of delta u plus I delta v over, now we have an I delta y. Okay, good. And these two expressions are going to have to be equal for that function to be analytic. So we're going to take these and set them equal to each other and derive a set of conditions that has to be true for that function to be analytic. That's where we're going with this. And now you kind of see this funny thing that's going to happen because I'm dividing by I. If you like, I can multiply top and bottom by, let's say, I times I, and if I multiply top and bottom by I times I, I'm going to get some pluses and some minuses and some weird stuff. I'll just write down what happens. So I'm going to get, this is going to be a partial u partial y. So that's a partial u partial y, but it has an I out front. Here, I times. I don't want to like confuse everybody. I'm going to multiply each top and bottom by I. And so this becomes a minus 1. So this is a minus. And here, this I delta u becomes I delta u, and this I times I delta v becomes minus delta v. So I have I delta u minus delta v. That's what happens when I divide by I, apparently. Okay, remember, because the delta y had an I out front. And so now if I take the partial derivatives, the real thing is minus partial v over minus partial y. That's just partial v partial y. And the imaginary part is going to be, again, minus I partial u partial y. Partial u partial y. Okay. So that was a lot. Again, what we're trying to do is we're trying to, essentially, we showed the example of what weird thing can happen when you approach from different directions and have a non-analytic function when they don't equal. So we're trying to derive conditions for what has to be true for the real and imaginary part of my function for these two directional derivatives to be equal to each other. And the two directional derivatives, if I approach on the real or the imaginary axis, are these two partial derivatives of u and v. And so now what we're going to do is we're going to equate the real parts of these. Those have to be equal. And also the imaginary parts also have to be equal. And these are going to give me my two Cauchy-Riemann conditions. So for my function to be analytic, I need partial u partial x to equal partial v partial y. That definitely has to be true. And I need partial v partial x, or let's say, partial u partial y to equal minus partial v partial x. These are my two Cauchy-Riemann conditions, super duper important. Cauchy, some people think it's Cauchy, it's Cauchy, and Riemann. And how many M's and R's does Riemann have? Riemann. Let's say it's Riemann. I think there's probably two M's. I'll just put another one there. Riemann. OK, the Cauchy-Riemann conditions. So Riemann was Gauss's student, I think. Very, very, very bright geometer. Cauchy was probably one of the most influential people in making complex numbers real and concrete for us humans, along with Euler. So remember, before Cauchy and before Euler, people thought that imaginary numbers were just some useful computational trick, but they didn't really mean anything. They weren't real. And Cauchy helped to solidify that complex numbers and complex functions are actually, essential parts of reality. They are solutions of physics. They are real, concrete objects. And this is one of the most important conditions in all of mathematics, are called the Cauchy-Riemann conditions. If the real part u of my function and the imaginary part v of my function satisfy these two conditions, what that means is that my derivative exists and will be finite regardless of what approach I take this delta z goes to 0. If I go in the real axis or the imaginary axis, if these two conditions are true, then these two expressions will be equal, and my df dz is well defined without having to specify what direction I took that derivative in. So this is a huge deal. Okay, huge, huge deal. The Cauchy-Riemann conditions are necessary and sufficient, well, they're necessary conditions for a function to be analytic. And if my function is single valued, and these partials exist, then they're also sufficient conditions. Very, very important. Okay, so where is this going? So that's kind of it. We're talking about complex functions that we can do calculus on. They're called analytic, and they have these properties. Basically, f prime of z exists and is well defined regardless of what direction I take that derivative in. These Cauchy-Riemann conditions have to be true for my derivative to be independent of the path I take dz to 0 on. And that is necessary and sufficient to have a well-defined derivative so that I can do calculus. Functions like polynomials, exponentials, cosines, and sines, and even the logarithm on its principal branch away from the origin are examples of analytic functions. Weird functions like the complex conjugate or singular, points at a singularity or cliffs or cusps are typically not analytic functions. And why do we care about these analytic functions? What do they allow us to do? So analytic functions are super neat because analytic functions, essentially what I'm going to show in the next lecture, very, very important lecture, is that if the function is analytic, if f of z is analytic, then the real part and the imaginary part solve Laplace's equation. Then del squared u equals 0 and del squared v equals 0. So these analytic functions, the real and the imaginary part, solve the Laplace partial differential equation. These are called harmonic functions. The real and imaginary part of an analytic function are called harmonic functions. These are harmonic. And they're harmonic because they're the solutions, of guitar string waves and sound waves and all of the physics that you're used to, that involve kind of partial differential equations. The basis functions that we use to represent all solutions of simple linear PDEs that we're familiar with are these harmonic functions like sines and cosines and things like that. The Fourier series are harmonic functions that are the real and the imaginary part of complex valued analytic functions that happen to solve Laplace's equation. So that's super duper important. And before computers, this is important, before computers, we had to solve these PDEs using by-hand solutions pulled from the real and the imaginary part of complex functions. So if you go back in time 50 years, complex analysis was not a 2-week boot camp on YouTube. It was a full semester course that you took. It was a 15-week course to get so good at dealing with these functions that you could actually solve really hairy, gnarly PDEs by hand. Okay, and then the last thing I'll show you is that if a function is analytic, there are some really nice properties of solving closed contour integrals of f of z dz over a closed contour that's inside this domain. That will equal 0. So that's a really, really important property of analytic functions, is that it's really also easy to integrate them over closed loop. Just like we have conservative functions in physics, functions that conserve energy, like the potential function, the gravitational potential, or the electrostatic potential, hint, solutions of Laplace's equation. If I take a frictionless roller coaster and I go around that roller coaster and I end up where I started, I have neither gained nor lost any energy. And that's kind of this generalization that all of these closed contour integrals inside of an analytic domain of an analytic function will add up to 0. They're kind of conservative functions. Okay, that was a huge amount. You'll probably have to go through parts of this again if you really want to master this. This is not trivial stuff. If you want, I'm going to probably erase this in fast forward and show you that z squared is in fact analytic, but this is kind of the end of the video. So in the next video, I'm going to show you that if my function is analytic, it does solve Laplace's equation. Very, very important. All right, thank you. Okay, so right now I'm going to show you that the polynomial z squared is analytic because it is single valued and because its derivative f prime exists regardless of the direction that I take delta z goes to 0. Okay, I erased the board. I actually tried to do this and got myself completely stuck. These things are not always obvious or easy, so I get stuck all the time doing this kind of stuff. Maybe I'll leave that part in and you will have just seen me fast forward through scratching my beard for about 5 minutes, but it's actually pretty simple. What I'm going to do is we're going to take the function f of z equals z squared. Again, this is a single valued function. There's only, if I pick a specific z, there's only one number z squared. Unlike z to the 1/2, which has 2 values, z squared has 1 value, so it's single valued. And what we're basically going to do is we're going to compute, we're basically going to show that the Cauchy-Riemann conditions hold so that the derivative along the real axis and the derivative along the imaginary axis are equal to each other. Good, so f of z equals z squared. And I'm going to write this out in the real part plus the imaginary part. So this equals, it's like a x plus I y quantity squared. So the real part's going to be an x squared plus an I y quantity squared, which is minus y squared. That's the real part. Plus I times, xy plus yx, so that's I times 2xy. And so this is my real function u. And this is my imaginary function v. Good. And I think what I'm going to do, because we know, if we approach on the real axis, then the derivative is equal to this sum of partials. And if we approach on the imaginary axis, the derivative is equal to this sum of partials. I'm just going to compute these two partials and confirm that they're equal to each other. Okay, so along path 1, if I go on the real axis path of delta x goes to 0, then df dz, which is essentially df, the limit of delta f over delta x, this is going to equal partial u partial x plus I partial v partial y. And partial u partial x is 2x plus I, and partial v partial y is, again, 2x, correct? 2x. Did I do that right? Oh, well, I'm stupid. This is partial v partial x. Sorry, I'm not stupid. No one, like, when you make a mistake, you're not stupid. It was a stupid mistake. This is not partial v partial y here. It's an obvious mistake. Dumb mistakes are the best mistakes because they're easily fixed. Okay, that's what I always tell my students when they, finally found a bug in their code and they feel, like it was the simplest mistake and they've been stuck on it for 2 weeks. Those are the best kinds of mistakes because they're so easy to fix. Okay, so dumb mistakes are the best mistakes. This wasn't partial v partial y, it's partial v partial x. And partial v partial x, if I take the derivative, I get a 2y. That is more like what I'm looking for. This becomes a 2y. And 2x plus I2y equals 2x plus iy, which is 2z. Beautiful. Okay, that's what I expect my derivative to be. I expect my derivative f prime of z intuitively to be 2z. That's what we expect from regular calculus. So that's true when I do this way. Now let's try it on the imaginary axis. Axis. Okay? And I think it's important for you to see me make mistakes because, I make mistakes all the time. When I do this live for my students, sometimes I actually prepare only a certain amount so that they can see, how you derive things on the spot and reason on the spot. Because it's like too easy to think that your instructors just know everything and they remember everything and they always can solve the answer. That's probably not the case. Okay, we all make mistakes and we all have to be catching ourselves constantly. So now if we compute this on the imaginary axis, we have dfd z equals, this is just a straight line d, this is a total derivative dfdz. It equals partial v partial y minus I partial u partial y. Okay, good. Partial v partial y is 2x, good, minus I partial u partial y is a minus 2y, so that's a minus 2y. And again, 2x plus I2y is just 2z. So essentially what this shows is that because these two equal each other, this derivative, this function f of z equals z squared, the derivative is 2z regardless of what direction I take it in the complex plane. Now, if you want to get really, good at this, and you have 30 minutes to do this on your own, I would recommend, we just took the derivative in the real direction, we just took the derivative in the imaginary direction. Confirm for yourself that if you take the derivative in, this direction of like delta x equals delta y goes to 0, or in this direction, those also equal 2z. It's a little bit hairy. You're probably going to have to Taylor series expand this thing and keep track of a bunch more stuff, but it definitely is true. And that's kind of how you would prove that this Cauchy-Riemann condition, that the real and the imaginary direction derivatives equal each other is necessary and sufficient, that the directions will, that the derivative is well defined for any direction delta x and delta y go to 0. For any path I take where delta x and delta y go to 0, they're all going to equal each other if these two conditions are true. Whew, okay, so next lecture we're going to prove that the real and imaginary parts of these analytic functions are solutions of Laplace's equation called harmonic functions, and we're going to derive some kind of important consequences of that. All right, stay tuned. Thank you.